Hello, this is Mr. P, and today we're going to talk about parametric equations. Parametric equations are going to be a little different from the rectangular equations that we've been dealing with, because up till now, rectangular equations have been basically of the form y equals a function of x. So here's an example of a rectangular equation. We have y equals this function of x. And if we look at the visualization or the graph of that equation, we would see a parabola. It's y equals x squared. It's going to be a parabola. And the idea of y equals a function of x is the input and y is the output. So in other words, if x is such and such a value, then y is such and such a value. With the parametric equations, we're taking, instead of y being a function of x and y are both going to be functions of a third variable, and that variable we call the parameter. Usually you're going to see t is your parameter. T usually is used for time as a parameter, and so you're going to have x is some function of time and y is some function of time, some function of t. Therefore, the input-output works, at a certain time. This is the x value, and this would be the y value. So rather than y being a function of x, you have x and y are both functions of the other variable, which is the parameter. And these are the parametric equations for that same curve. And the important thing to understand with parametric equations is they have more information in them than just the rectangular equation. Even though the curve looks the same curve, or the curve is the same curve, parametric equations also tell you where on the curve it is at a certain time. So it gives you motion along the curve, which is called curvilinear motion. We have two variables for the position, the x and the y, and we have one variable for time, which is the t. So this graph also has an orientation to it, and you can sort of see there, it's a little small, but you can see there's an arrow there. That shows that as time progresses, as time moves in a positive direction, the movement along the curve goes in this direction denoted by the arrow. So by using parametric equations, we can actually evaluate weird-looking curves like this, more exotic curves, which we call a plane curve. And this would definitely not be a function if we tried to use the vertical line test or something like that. But if we write this as a parametric function, write it as parametric equations, then each of the equations would be functions of time. So we would be able to use all the tools that we've been using so far with regards to functions. So even an exotic looking curve like this can be analyzed using parametric equations. So let's jump into some problems and see what we need to be able to do with these. First of all, we need to be able to discuss these curves. So they want us to discuss the curve defined by these two parametric equations. It's our x equation and our y equation, both of which are functions of t, which stands for time. Now, within our parametric equations, we're usually only interested in a certain interval for the parameter. Like here, we only care about time from -2 to +2. And it's okay to have a negative value for t, for time, because this is all with respect to a certain event. So t being -2, that would represent 2 seconds before some event, and t being a +2 would be 2 seconds after the event. Matter of fact, in NASA, when they're doing a countdown to a launch, they say t minus however many seconds till the actual launch. So you've heard this notation before. Now, when we discuss the curve, there are 5 things we need to do to accomplish a full analysis of these parametric equations. And these are them. First, we're going to identify the curve type, graph it by hand, show the orientation, graph with the calculator, and identify the equation. That is the rectangular equation that is equivalent to the parametric equations. And that last step is typically the hardest one, so we'll do that one last. As a matter of fact, we're actually going to do the second step first. We're going to graph it by hand. And to do that, we're going to use a table of values. So Instead of being just x and y, though, we're going to have t, x, and y, where t is the input, and then x is an output, y is an output. So since our interval goes from -2 to +2, it would make sense that we would want values of t that are -2, -1, 0, 1, and 2. So I take, starting out with the -2, I substitute that into the x equation. -2 squared is 4, 4 times 3 is 12, so x is 12 when t is -2. Now in the y equation I also substitute -2. -2 times 2 is -4, so y is -4 when t is -2. So now the interpretation here is at time -2, these are the coordinates of whatever this is tracking. Might be a particle, and might be, for our uses now, we'll call it a particle. So this particle is at these coordinates at this time. And I do that with my other t's. I input into the x's and the y's, and I get these as the values. And then we're simply going to graph these, which means we're going to plot these 5 points. So looking at a graph, I plot 1, 2, 3, 4, 5 points. Our graph is not quite complete yet, but at this point we do have enough information to identify our curve type. Hopefully by now we plot the 5 points, we draw a smooth curve through those 5 points, and you should recognize that this curve type is a parabola. So identifying the curve type, the curve type is a parabola, and now graphing by hand, we plot the points, draw a smooth curve through those points, but then we also need to show the orientation. And notice this parabola doesn't go on forever off to the right. We are only graphing this from t being -2 to t being +2. So this is a self-contained graph. It does have a initial point and a terminal point. And it's that initial and terminal point which is going to help us to show the orientation. Notice how we start at 12, -4, which is this point, and we end up at 12, 4, which is this point. So as time is flowing in the positive direction, this is the direction that we're moving along the curve. So to show the orientation, I need to simply add some arrows along the curve to show that is the direction of the movement. Alright, next we need to be able to put this into a graphing calculator, so let me walk you through that. We're going to use the TI-84. First thing we need to do, of course, is go into mode. Always check your mode before every problem. And in our mode, we're going to be in parametric mode, which is PAR. Most of what you do in the calculator is function mode, but now we should be in parametric mode. Also, it doesn't say whether to be in radians or degrees, so by default we want to be in radians if it doesn't specify. Alright, so with that we're going to go to y equals, which now is x equals and y equals, because we have an x equation and a y equation. So we want to make sure you have no equations in now. If you have anything in there now, just clear it out. Plus you want plot 1, plot 2, and plot 3 to be off, in other words not highlighted. If they are highlighted, you arrow up to them, hit enter to toggle it on or off, and then arrow back down. So for our equations, our x equation, just to remind us, was 3t squared. So here we're going to do x is 3. Now t is that same button we use for x in the function. Matter of fact, you say x, t, theta, or n. Which letter it gives you, or which variable it gives you, depends on which mode you're in. It'll give you x if you're in function mode, t if you're in parametric, theta if you are in polar, and n if you're in sequential. So if I hit that button, it does give me a t, so it's 3t squared. And then I can hit enter or the down arrow to get to the next line. And the y equation is y equals 2t, so 2 times t. And for our window, we don't want to go to the graph just yet, because for our window we need to identify the t min and max, and this is a lot like in polar equations when you had theta min and max. We want to think of the interval. What values of t do we care about? We care about from -2 to +2. That's given. That interval is given to us. So our t minimum is going to be -2. Make sure you're using the negative button, not the minus button. So -2, and then enter or down arrow, to +2, enter. And now t-step acts just like theta step did in the polar equations. It's going to be the trade-off between detail and speed of graphing. So, for example, if I did 0.1, we're going to see how the graph is. In other words, that means it's going to graph the point at t is -2, and then t is -1.9, then -1.8, and it'll plot the points that way. The lower your t-step, the more detailed your graph will be, but it'll be slower to actually create the graph. So we're going to start at 0.1 and then adjust it accordingly. Now the rest of the values I don't really care about because I have a nice self-contained graph here, so I can simply use the zoom fit feature, which is zoom 0 is zoom fit. So you can either hit the number 0 or arrow down and then hit enter. Either way, this is going to be your graph. Now notice how our parabola looks a little scraggly as it's coming around here. It doesn't quite look that smooth. So I could go into Window, come down to the t-step, and use 0.01 and get a better looking graph that way. And notice how now we get a little bit of a smoother curve. And that wasn't too slow, so I think 0.01 will be a good overall setting for us, because it is a trade-off between detail and time to actually make the graph. All right, so that is our graph. For the orientation, now if I needed to find the orientation, first of all, I could have watched it as it graphed it. It did show the orientation. But let's say it was already graphed and I didn't notice how it graphed it, or it graphed it so quick I didn't see it. You can always go to Trace, and the trace is going to start you off at your lowest t value. You can actually see in the corner there the blinking cursor. So it starts at time is -2, and it gives you the value of that coordinate. And then notice as I hit right on the arrow button, notice how my cursor is actually moving to the left. So as I hit right on the arrow button, the cursor is actually moving to the left. That's because the arrow buttons doesn't move the cursor on the screen. The arrow buttons move the cursor with respect to that input. So as time is going to the right, as time is increasing, the movement on the curve is this way. So you can watch the movement of the cursor, and that will help you find your orientation. Also notice when you're in Trace, any number that you start to type in, it will take as the input is of t. So let's say I want to know, well, where's the particle at time 1.5 seconds? So if I just type in 1.5, notice how it takes it as the t value, and when I hit enter, it jumps to that point and gives me the x and the y value. So at time 1.5, even though this wasn't one of our data points, once we find the model, we can do interpolation. X is going to be 6.75, Y is going to be 3. Also notice that, unfortunately, if we go into the second trace, which is the calculate menu, in parametric mode, we do not have the minimum or maximum or the intersections. We don't have those tools in parametric mode. So we're going to be using more of the trace to do our analysis. All right, so let's go back to the graph, and we're going to put the calculator aside for a second. We're going to come back to it a little later. But we've graphed it with the calculator. So the last thing is to identify the equation. We want to change the parametric equation into a rectangular equation. And when doing that, there is sometimes the ability to have like a shortcut. If you can find a relationship between the two expressions, then you can find an elegant solution and a quicker way to do it. But more often than not, you're going to have to just fall back on the process called eliminating the parameter. And eliminating the parameter means that we solve either one of the equations for the parameter, and substitute that expression into the other equation, and then you have the relationship between x and y. So here we do have the freedom to choose which one of the two equations we want to solve for t, and I think this one is a lot easier to solve for t. So when eliminating the parameter, I'm going to start with y equals 2t, divide both sides by 2, I get t equals y over 2. So now I take the other equation, and instead of t, I'm going to substitute in, so I have x equals 3t squared. Now instead of t, I'm going to substitute y over 2. And then I can clean it up a little bit, and we have, there's our relationship between x and y. So it's basically x equals a y squared, so we should recognize that as a parabola. That will be a horizontal model of the parabola. Okay, so that is fully discussing the curve, finding all 5 of those items. Now I talked about an elegant solution. Let's look at some trigonometric problems. And here we're just going to find the rectangular equation for these parametric equations. And this one does have an elegant solution, which I want to show you. I'm actually going to work this problem both ways. So if you can find some relationship between the expressions, then sometimes you can save some time and take a little shortcut. So here, sine and cosine, well, those are related ideas. Matter of fact, the relation between them is the Pythagorean identity. So you have cosine squared plus sine squared equals 1. That is our Pythagorean identity. So what we're going to do is we're going to divide through by a, so that we get here cosine of t is going to be x over a. And in this one, sine of t is going to be y over a. And then I have expressions I can now substitute in for sine and cosine. Remember, if cosine is x over a, I make that substitution. If sine is y over a, I make that substitution. And now I simply clean this up algebraically. I'm going to clear the fractions, multiply through by a squared. And this gives us something that we should be very familiar with. X squared plus y squared equals a squared. That will be a circle centered at the origin with a radius of a. And the graph of that would look like this. From the center, which is the origin, I have the points a comma 0, 0 comma a, negative a comma 0, and 0 comma negative a, although that one's not shown. And the last thing to figure out would be the orientation. And with that, you can sort of see that the role of t is it's the argument of the trig values. So t is also representing an angle. Since you're taking the sine and cosine of it, it's going to act like an angle, which means as angles get larger, it's going to go this way around the circle. Just like we think of the natural movement along the unit circle, it's going to go in the counterclockwise direction. Barring that, if you didn't recognize the role of the t, you could always just plot a few points with t being a larger number, increasing your t to see which way you move along the equation or along the curve. Notice how your rectangular equation does not give you that information. You have to go back to the parametric equations to get that orientation. Alright, now it's great if you can find an elegant way to solve the problem or convert it to rectangular, but sometimes you just cannot. So we're going to take the same equation, and I'm going to go back and we're going to do this one by eliminating the parameter, which will be a good review on solving trig equations as well. Alright, looking at the two equations, it doesn't really matter which one I solve for t because they have equal complexity, it looks like. So I'm just going to solve the first one for t. First I'm going to divide through by a, so cosine t equals x over a. But then I don't really want cosine of t, I want just t. So I undo cosine with inverse cosine. Or in other words, I'm going to take the arc cosine of both sides. And when I do that, the arc cosine of the cosine is just whatever the argument is. So I get t equals the arc cosine of x over a. So now I have an expression that is equal to t. I'm going to use that to substitute into the other equation. So instead of y equals a sine of t, I'm going to say y equals a sine of this expression. So y equals a sine of r cosine of x over a. And now the understanding I want you to have with this equation is that the blue thing here represents an angle. It represents an angle because it's the argument of this trig function. It also represents an angle because it is arc cosine. Remember that geometrically, trig values geometrically represent the length of a segment, and inverse trig values geometrically represent an angle. And your argument is an angle. So more specifically, though, this argument here represents the angle whose cosine is x over a. That's how we read arc cosine. It's the angle whose cosine is x over a. Now, I can make a visualization of that. I can, and it's not the only way it can happen, but I can make a triangle with an angle that I'm going to call theta to make a notation a little easier. So I have an angle who, if I were to take the cosine of that angle, it would be adjacent over hypotenuse, would be x over a. So this triangle is one possible triangle to represent that angle. Now the interesting thing here is I don't actually care what the measure of that angle is, because that's not what the equation is asking for. It wants the sine of that angle. So once I know two sides of a triangle, I can always find the third. The leg of a right triangle is going to be the square root of the hypotenuse squared minus the other leg squared. Or in other words, a squared minus x squared, and then take the square root. So once you know two sides of a triangle, you can always find the third with the Pythagorean theorem. And now, since I can find the sine of that angle, then I take y equals a times the sine of this angle is going to be opposite over hypotenuse, or the radical over a. So I can substitute that in. So y equals a sine theta now becomes a times the sine of theta is that radical over a. And conveniently, the two a's cancel themselves out. So we get just y equals that radical. And to put it in a more familiar form, I could square both sides, which would give me y squared equals a squared minus x. I can move this x term over to this side, which makes it positive, and that would give us x squared plus y squared equals a squared, which was what we wanted because we worked the problem already and that was our answer. So you see, sometimes if you can find that relationship, you can find an elegant way to solve the problem. But if not, you do have to be able to work the algebra to eliminate the parameter. All right, the other big usage of these parametric equations is going to be projectile motion. And if you remember from physics, you've seen these two equations in physics, which means you've actually dealt with parametric equations already, just they weren't called parametric equations. So here in physics, projectile motion is any motion that is acted upon by gravity. So your x being a function of time and y being a function of time, you can tell after a certain amount of time where that object is going to be. So your x equation is, now the v sub 0, that's read as v naught, and then cosine of theta times t. So it's v naught cosine of theta times t. Notice it's just three things being multiplied, so you could actually move the order of those terms, but it's v naught times cosine times t. And y is this equation. The g is the gravitational constant. Now, that'll be different depending upon whether you're working in feet or working in meters. If you're working in meters, which you usually do in most physics classes, g will be 9.8 if you're dealing in meters. But if you're working in feet, then the gravitational constant will be 32. Gravity on Earth is 32 feet per second squared. So make sure that you have the right gravitational constant. Some word problems will be in meters, some word problems will be in feet. Also, some will be in radians, some will be in degrees. Make sure you're in the proper modes when you're working those problems. And v naught is still your initial velocity. That represents your initial velocity. Theta is that initial angle, or the direction in which the object is thrown or shot or dropped, or that's your initial direction. And then t again is time, and h is the initial height. So you can even use these equations if you had a cannon, for example, on the top of a hill, and it shot a cannonball down into the valley. That initial height above the ground in the valley would be a part of the equation. All right, so let's see how we use these equations, and we're going to do that, of course, with a word problem. Now, it's an intimidating word problem at first, but it basically can be done step by step. It's pretty straightforward. Suppose that Jim hit a golf ball with an initial velocity of 150 feet per second. Well, right away, that fact that I see feet means that my gravitational constant is going to be 32. So that's the red flag that gives me that gravitational constant. So it's 150 feet per second at an angle of 30 degrees. Once again, we're working in degrees this time, not radians. And see the figure, this is the visualization of that. Okay, first question, we'll just take them one at a time. Find the parametric equations that describe the position of the ball as a function of time. Well, that's nothing more than taking these two equations and substituting in the values we know. So that would look like this. We know that the initial velocity is 150, that's v naught. Our theta is 30 degrees, which is this angle here. The initial height is 0 because the ball starts on the ground. And gravity is 32 because we are working in feet. So substitute those values in, we get that x is 150 cosine of 30 degrees times t. And here we can simplify it because the cosine of 30 degrees is the square root of 3 over 2. So 150 divided by 2 is 75, so it's 75 times the square root of 3 times t. And for the y equation, we have, again, g is 32. V naught, or your initial velocity, is 150, and we times the sine of 30. Now the sine of 30 is 1/2, so 1/2 of 150 is 75. That's where we get that term. And negative 1/2 times 32 is negative 16. So it's negative 16t squared plus 75t. That's your y equation. All right, so those are the parametric equations. That answers part A. Part B asks, how long is the golf ball in the air? Well, how long means they're asking for a value of t. And we want to find what is the value of t when the ball hits the ground. Because that'll tell us how long it starts out on the ground, that's t0. And then you hit it, the ball's traveling. As soon as it hits the ground at some certain time, then that'll tell you how long it's been in the air. So the idea here is we can look at the equation for the height, because I want to know when does that ball hit the ground. If the height is 0, then the ball hits the ground. So, and this is a quadratic equation, so it's going to have two answers, but we should expect that because the ball is at the ground at time 0, and the ball's on the ground at some other time down the road. So if we take negative 16t squared plus 75t equals 0, we set the height equal to 0. And your first attempt at a quadratic equation should always be to try to factor if possible. That'll be the easiest way. And here both terms have t, so you factor out t. Now we can use the zero product property, either t equals 0 or that parenthesis equals 0. Solving that parenthesis for 0 gives you t equals 75 over 16, which is not approximately, which is exactly equal to 4.6875 seconds. So these are the two times where the ball is on the ground. And this one we expected already. This was the one we were looking for. So the ball will strike the ground after 4.6875 seconds. Part C is a two-part problem. They want to know when is it at its maximum height. So again, when means what's the value of t. And then they want us to determine the maximum height, which will be a value of y. Y representing the height. All right, so if we think about that, there's actually two ways we can do this. To find out when it's at its maximum height, we can use the fact that we should realize that this quadratic equation is going to be a parabola if you graph it. Now, we did learn earlier that there is an equation to find the x value of a parabola. It's negative b over 2a. When you have your equation is ax squared plus bx plus c, then the x value of the vertex, because the vertex is where you have a maximum or a minimum, it's x equals negative b over 2a. So we can use that. Negative b would be the negative of 75 over twice the a, which is the 16. And we put that in, we get 2.34375 seconds. That's one way to do it. Another way to do it is to recognize that we have a parabola where it started out on the ground, it went in the shape of a parabola and landed on the ground. So a parabola is very symmetrical. So the axis of symmetry, which goes through that vertex, same y values will be equidistant from that axis of symmetry. So really the vertex is going to be in between these two. So if you simply took the 4.6875 seconds divided by 2, you're going to get the 2.34375 seconds. So if you understand the geometry of the problem, you could have just divided that number by 2 to get that. Or x equals negative b over 2a. Now, once you know when it occurs, when the maximum height occurs, to find the height, you simply input that value of time into the equation for height, which again is this equation. So we substitute that in, we use the calculator this time, and we're going to get approximately 87.89 feet. This time we did actually round. So that'll be the approximate maximum height of the golf ball, and that occurs at that time. All right, let's look at part D. It says determine the distance that the ball traveled. So I want to know the distance from when we struck the ball to where it landed. We're assuming there's no rolling effect afterwards. So when it lands, it stops. So for that distance, we want to know when the ball landed. We already know that at 4.6 seconds. So we can simply look at the equation that tells us where the ball is, where horizontally it is, and input the 4.6 seconds. That'll tell us when where it is when it hits the ground. So doing that, we simply take the x equals 75 root 3 times time, input for the 4.6 seconds for time, and you're going to get approximately 608.92 feet. And then finally, the last one is using the graphing utility to simulate the motion of the golf ball by simultaneously graphing the equation. So we're going to take the graphing calculator and double check all of these values. So going back to our, let's look at the graphing calculator, going back here. First, I want to go to mode, and I want you to build the habit of checking your mode before every problem. Because like we said before, sometimes we're in feet, sometimes we're in meters, sometimes we're in radians, sometimes we're in degrees. And if you remember in this problem, we were in degrees, so I am going to go ahead and change my mode to degrees. This is a habit I really want you to get into, is check your mode before every problem. So now we're going to go back to y equals. I'm going to clear out these equations because they no longer apply. And my new equations for x, this equation was 75 square root of 3, close parenthesis, and then times t. So 75 root 3 times t, that was my x equation. And the y equation was negative, again negative not minus, 16t squared plus 75t, if I remember that right. Yeah, that's correct. Alright, so we have our x and our y. We're going to look at our window. And for t min and t max, well, we have a little bit of a leg up here. I know the ball lands at 4.6 seconds. So we want to select t values that make sense to us. And I'm just going to choose from t being 0 to t being 5. Oop, hold on a second. So t equals 0, enter to get down to the next line, and then t equals 5 will be my maximum. I only care what happens between time 0 and time 5. The step 0.01 seemed to work well for us last time, so I'm going to leave it at that. The rest of the values I don't care about because I'm going to go zoom 0, which will fit all of our data from time 0 to time 5 within one window. So this is our parabola. And pretty good detail, didn't take too long to graph, so I like that 0.01. Now I would like to comment here, and this is sort of optional, but I can use this window to answer all of the questions. However, I'm a big advocate of being able to visualize these problems. And this is not a realistic view of the flight path of this golf ball. And it's very easy to get a realistic view of the flight path. Once we have all the data we want in this window, or all the points we want, we can, after we do zoom 0, which is zoom fit, we can now do zoom square, which is zoom 5, and that will square the x and y axes. In other words, change the scales so that they are the same. And you see this gives you also a parabola, has all the points that the other graph has, but this is a realistic flight path of the ball. And especially when working word problems, I believe having a correct visualization is beneficial. Alright, so with this, we're going to double check our first thing. Well, we already had the equation, so part B, we want to make sure that this does strike the ground at 4.6875 seconds. So I'm going to go into trace. It'll take t as I input, so I can simply do 4.6875 and add that t. When I hit enter, it jumps to that point and says, yes, look, the y value is 0. So there's no height. So that is now a confirmed figure. As a matter of fact, while we're on this point, it also confirms this, because this was the distance. So going back to here, the height, or the time when it landed, was at 4.6 seconds. That's verified. But also the x value was 608.92. That's the distance that it traveled, was approximately 608.92. So we can verify both of those. And now to find the maximum height, we said the maximum height occurred at 2.34375 seconds, and the maximum height was approximately 87.89 feet. So to double check that, I can put in 2.34375, which it takes my t value, which is what I want. And when I hit enter, it jumps to that point. And it says, yes, the height was 87.89 feet. And you can see by the graph that, yes, it looks like it is at the top of that parabola. And incidentally, although they didn't ask for it, that maximum height did occur at approximately 304 feet from where you hit it, which again should make sense with our symmetry, because that will be half of the 608 feet. So don't forget the symmetry that occurs in these parabolas. It can be good time savers. All right, and with that, they do want to stress, of course, that you use that zoom square so you have a realistic looking flight path. And if you want to get a little tighter on your data, you could have used 4.7 as your maximum. I used 5. Either way, it's fine. But that's how we use the calculator. And we're done.